Hello class 12. The topic that we are going to discuss today is basically about resonance. Okay, in this video itself we are going to also discuss about something called a bandwidth and thereby sharpness of resonance and Q factor. Okay, so in the last video we studied about LCR circuit and we studied about the power for different kinds of circuits also, basically for an LCR circuit, and we saw that the power for LCR circuit is equal to IRMS VRMS into cos phi, where cos phi is called the power factor of the circuit, remember. By the way, this power is also called average power. Since we started, if you check the video for or the derivation for power, we started with instantaneous value of power. Okay, then after we calculated for one complete circuit, we saw for one complete circuit sine 2 omega t was 0, cos 2 omega t was 0 and sine squared omega t was half. Okay, that was for one complete circuit. Since it was for one complete circuit that we were calculating, so therefore this P is also called average power, remember. Okay, I forgot to tell you that in that video itself. Okay, do you remember this is also called average power, but you can simply call it power, so to say. So the power we saw for LCR circuit is IRMS VRMS into cos phi. Now phi is the phase difference between the value of the current and the effective voltage, the phasor diagram for LCR circuit. Please go and check that. So therefore, instead of cos phi, we can write base divided by hypotenuse. So base is VR divided by the effective voltage V is equal to square root of VR squared plus VL quack VC whole squared. Okay, this term, this symbol is not called a quack. Alright, it's only for us that it's called a quack, remember. So the power factor can be rewritten as, not the power factor, the average power or simply the power can be rewritten as I naught by root 2, because IRMS is the peak value of current divided by root 2, don't forget. Likewise VRMS is V naught by root 2 into, now at any instant if current I is flowing, you will get a I into R over here from Ohm's law, and from the square root also you will get I, so I, that I, these two I in the numerator and denominator, they divide each other out. I hope you can visualize, and therefore we get R divided by square root of R squared plus XL quack XC whole square. Now specifically at resonance, since XL is equal to XC, so therefore we've seen that at resonance when this happens, okay, what is the denominator over here? The denominator over here is the impedance of the circuit. Alright, so impedance of the circuit at resonance will simply be equal to R. That is the effective resistance offered by the LCR circuit to the flow of alternating current is the least at resonance. Alright, so therefore at resonance the denominator becomes simply R, so that R and this R, they divide each other out, and therefore we get maximum power at impedance. Okay, for the case of resonance, not an impedance, for the case of resonance, since the impedance is the least, which is equal to R simply, therefore the power will be maximum. Okay, so the maximum power is I naught by root 2 into V naught by root 2 simply, which can be written as P max is equal to I naught V naught divided by 2. And don't forget also at resonance, since obviously XL is equal to XC, we've derived this, okay, the resonant frequency omega naught is equal to 1 by root of LC, or F naught is 1 by 2 by square root of LC. So this is all that we have seen for the case of resonance. Do remember these points especially. Alright, and don't forget at resonance the impedance is the least, which is equal to the value of the resistance in the circuit itself. As if at resonance, therefore, the circuit behaves, LCR circuit behaves as if there is no L and C, as if there is only a resistor. It behaves that way, so to say. Let us now talk about bandwidth and sharpness of resonance. But before we actually jump into this topic, let's try to understand this graph or this plot that I've drawn here. Now this plot is the graph of power delivered by an LCR circuit versus the angular frequency omega. And this peak of the curve corresponds to the case of resonance, at which point therefore omega naught is the resonant frequency, and this peak here is the value of maximum power, because at resonance you have maximum power. Or you can also say this peak is or gives the value of the maximum current, because for the case of resonance, what happens is the impedance offered by the circuit is the least and is equal to the resistance of the circuit itself. And therefore, since the impedance of the circuit for resonance is least, therefore maximum current will be flowing in the circuit. So, therefore remember, this is the plot of power versus angular frequency, or you can also say it is the plot of current in an LCR circuit, of course, versus the angular frequency. Alright, now before we discuss more things about this graph or things we understand or learn from this graph, let us quickly give a look at this mathematics. So at resonance, P max we've seen is I naught V naught by 2. So V naught, the peak value of voltage at resonance, can be written as I naught into R, where R is the resistance of the circuit at resonance number. So P max basically is I naught squared R by 2. Now I naught is the peak value of current, which can also be written as I max. So I max squared R by 2. Now here I have discussed about one specific case, that is when the value of current is I max divided by root 2, or so to say I naught divided by root 2. Now why have I spoken about this specific case? We'll talk about that later, but first let us give or pay attention to the mathematics for this value of current, that is I max by root 2. So the power corresponding to this value of current, let us find that. So power will be equal to, the value of current is not I naught now, it is I naught by root 2. So therefore instead of I naught or I max, we have I max by root 2 whole squared R divided by 2. So power I max squared R by 2 into 2, because root 2 into root 2 is 2, of course. So therefore the value of power corresponding to this value of current I max by root 2 is P max by 2. Okay, pay attention to this mathematics. Alright, but obviously you will not be asked about this mathematics, this is only for our understanding. So get one thing very, very clearly here. The value of power corresponding to I max by root 2 value of current is P max by 2. That is, the power, so to say, will be half of its maximum value. Okay, like I said, I'll tell you why I'm talking about that. Okay, so coming back to this picture again. Now, why are we speaking or talking about this case of resonance and LCR circuit? Where is it used in our everyday life? The case of resonance in our everyday life is useful in the case of a radio, or also in the case of a television. Why? Because inside a radio, see, this is a radio, alright, and this is the antenna of the radio. So it is extended up to here, and this is the knob that you use to tune the radio. Here is the knob. So obviously, in order to tune the radio, what we do is we rotate, we turn this knob. Alright. So what are we doing actually here? When we turn the knob of a radio, what are we doing? We obviously are going to set the radio at different frequencies, or so to say we want to listen to different channels. Alright, so we rotate the knob. But what is technically happening is, when we turn the knob of the radio, we are changing the value of the capacitance or the value of the inductance inside the radio. Because inside any radio, we also have an LCR circuit. Okay, so when we turn the knob, what we are doing, like I said, is we are changing the value of the capacitance and the inductance of the circuit, not the resistance. Resistance value inside a radio cannot be changed. Okay, So we know the frequency or the resonant frequency for LCR circuit is given by omega naught, which is square root of LC. So by changing the value of the capacitance or the inductance, we are also changing the value of the resonant frequency of the LCR circuit, or on the whole, the frequency of tuning of the radio. Alright? Now, furthermore, this antenna, or rather the radio on the whole, is a receiver. Receiver of what? Receiver of informations in the form of electromagnetic waves. So in this air here we have so many different kinds of electromagnetic waves. We are surrounded by electromagnetic waves everywhere, so to say. So this antenna also is surrounded by so many different electromagnetic waves coming from all possible directions. There are so many electromagnetic waves, bringing about some kind of information, of course. So every electromagnetic wave is coming from a particular, station, radio station or FM channel or whatever it be. Alright? Now, what do each of these, electromagnetic waves they want to do? Each of these electromagnetic waves, they have a certain frequency, of course, and these different electromagnetic waves, they want to, so to say, resonate with your radio. Alright? So when you turn the knob of the radio and you set the radio at a particular frequency, say you set the radio at 102.3 megahertz. This is, by the way, the frequency of the FM channel in Kershon, okay, radio station. So you set your radio, you tune your radio, so to say, to 102.3 megahertz. And there is this wave, nice wave, having frequency 102.3 megahertz coming from the FM station in Kershon. Alright? So, since these two frequencies, this is 102.3 megahertz, mind you. So, since these two frequencies, they match, therefore, so to say, they resonate with each other. And when they resonate, you get a nice, clear, distinct sound. Okay? Because when these two frequencies, they resonate, this frequency coming from the radio station in Kershon, okay, this frequency produces, so to say, the maximum value of current and the maximum value of power. So therefore you get a nice sound, or you get to listen to all of the information coming from the radio station corresponding to this frequency. So this is what happens in resonance. Okay? But the story is not very nice and simple and easy going, so to say, because see, this omega naught is your 102.3 megahertz. So omega naught, the resonating frequency is 102.3 megahertz. But there are other frequencies as well, some over here and some way over here. There are other frequencies also. Say your resonating frequency 102.3 megahertz. This is say 102.5 megahertz, and this value is 102.1 megahertz. So as you can see, these two frequencies, 102.5 megahertz and 102.1 megahertz, they are also, so to say, producing an appreciable amount of current and thereby an appreciable amount of power. Now, these frequencies, they being producing an appreciable amount of current, your radio will receive information or signals coming from radio stations corresponding to these frequencies also, simply because these frequencies are producing an appreciable amount of current. So you will hear, so to say, a sum or a total of the information coming from all of these three different channels. Okay, so to say, you don't get a very clear and distinct sound, and you won't be able to make out anything. Okay, so obviously the thing is, you do not want this thing to happen. You want to get a very good good tuning or very good resonance, so that you get nice information, nice and clear information from one particular station. Okay, so how is that done? Now, to understand that, what we need to do is, first of all, we need to define how much is an appreciable amount of current, or so to say, how much is an appreciable amount of power. Okay, let's try to understand that thing first. So, what people have done is they've defined or set a standard value of power and a standard value of current, so to say, corresponding to that standard value of power, the current. So, the standard value of power that has been defined is P max by 2. So, people have said the value of current or the value of power greater than P max by 2 is appreciable amount of power. Now, you can see the current corresponding to P max by 2 value of power is I max by root 2. So, this is where this calculation is important. So, the value of current corresponding to P max by 2 is I max or I naught by 2 also. Sorry, I naught by root 2 or I max by root 2. So, people have defined any value of current greater than I max by root 2 is appreciable. And in fact, what happens is, okay, before we go into this, you can see, so this value is the P max by 2 or I max by root 2, and corresponding to this value of power or this value of current, you see you get two values of the angular frequency. Okay, this is called omega 1 and the other is called omega 2. Let me erase the values of frequency. So this is omega 2. Let me erase these parts. Alright, omega 1 and omega 2, these values of frequency corresponding to half the value of maximum power. Okay, so therefore, since omega 1 omega 2 corresponds to half value of maximum power, therefore omega 1 omega 2, they are also called omega 1 and omega 2. These things are also called half power frequency. Okay, omega 1 and omega 2. I hope I can erase this thing now. So I'm erasing. So omega 1, omega 2, they are called half power frequency, and to be more precise, omega 1 is called lower cut off frequency. Lower cut off frequency. And omega 2 is called upper cut off frequency. Okay, both together are called half power frequency since they correspond to the half of maximum value of power. Now, this difference between omega 1 and omega 2 is denoted by a delta omega. This is omega 2 minus omega 1, and this is called your band width. The difference between the half power frequencies, so to say, is what is called bandwidth, and delta omega is equal to the value of resistance in the circuit divided by the value of inductance in the circuit. This thing can actually be calculated, but the calculation is not there in your syllabus. It is there in your book though, okay, your textbook. If you want, you can check this, give it a look. Okay, the bandwidth is R by L. Now, what is the use of bandwidth? Let us check that. Now you can see that all frequencies lying between omega 1 and omega 2, that is all frequencies lying in this bandwidth, so to say, is producing an appreciable amount of current. All frequencies lying between omega 1 and omega 2, they are producing an appreciable amount of current, and thereby the channels corresponding to these frequencies lying between omega 1 and omega 2 will produce disturbance in our radio, which obviously we don't want to happen. So what is the solution therefore? The solution is the value of bandwidth can be decreased, because, or so to say, value of bandwidth can be decreased, meaning, can I erase these things? Of course I can, isn't it? So, value of bandwidth can be decreased, meaning this curve that we have is made sharper, so to say. It is made sharper. Alright, so this curve is made sharper by decreasing the value of bandwidth. Now what happens if the value of bandwidth is decreased? If the value of bandwidth is decreased, then the maximum value of power corresponding to this peak, your Pmax in that case will be over here. So this is your Pmax or Imax. Okay, and your Pmax by 2 will be somewhere over here. Your Pmax say over here. So this is your Pmax by 2. Alright, so here is your resonating frequency, here is the resonance being produced. Now, you don't have, if the bandwidth is reduced, you don't have much frequency. So omega 1 in that case will be over here, omega 1 is over here, and your omega 2 is over here. So this is your omega 1 and this is your omega 2. So you don't have much frequencies lying between omega 1 and omega 2. So if this is your, this omega naught is again your 102.3 megahertz, 2.3 megahertz. Alright, this will be somewhere over here, somewhere say it is 102.35 megahertz, and this frequency over here is 102.25 megahertz. Okay, so to say your lower cutoff frequency could be 102.2 megahertz and your upper cutoff frequency could be 102.4 megahertz. So anything lying between 102.2 megahertz and 102.4 megahertz is appreciable. And what is done is there will be no channels, FM channels or radio channels having frequency like this 102.25 megahertz or 102.35 megahertz. Okay, except for one value 102.3 megahertz. You don't have in between values like this. These kind of frequency are not allocated. Okay, so the only frequency lying between the lower cutoff frequency and the upper cutoff frequency, okay, will be your 102.3 megahertz. And thereby, when you set your radio to this particular frequency, when you tune your radio to this particular frequency, you will hear a nice clear sound from this, or from the radio channel or FM channel corresponding to this particular frequency. So this is how the the problem of disturbance is solved. So in order to get a nice loud clear sound, or so to say, in order to get good tuning or good resonance, the value of bandwidth should be decreased. And you can see the value of bandwidth can be decreased by decreasing the value of the resistance or by increasing the value of the inductance. Okay, so this is what is done, remember. Okay, so sharper the curve, better the resonance or better the tuning. Now there is one more factor which defines or which gives you an idea about how sharp or how flat the curve is. Okay, that factor is called, let me erase these parts. There's a bandwidth, don't forget. So let me erase these values of frequencies. So that factor is called the Q factor, or simply Q stands for quality factor. Q or quality factor. Now what does this value give you, quality factor or Q factor give you? It simply, like I already told, gives us an idea about how sharp or how flat the curve is, and we've come to know that sharper the curve, sharper the peak, okay, better the quality, better the resonance. So obviously we would like to have a good quality, alright, or good quality factor, Q factor so to say. So Q factor, mind you, is given by the resonating frequency divided by your bandwidth. Okay, or Q factor, quality factor. Now resonating frequency is omega naught divided by delta omega, so to say. Omega naught is how much? 1 by square root of LC divided by the bandwidth is R by L. Excuse me, R by L. So Q factor is equal to, so L by R into, you can do the mathematics itself. I'm tired of doing this. Okay, so Q factor is equal to 1 by R square root of L by C. So this is the expression for your quality factor, and like I told you, it gives an idea about how sharp or how flat the curve is. Now you can make out from the expression itself, lessen the value of resonance. What am I saying? R is your resistance and not resonance, okay? Delta omega bandwidth is R by L. So lesser the value of your resistance, more is the quality factor, and obviously more is the bandwidth. And greater the value of inductor, more is the quality factor, lesser the value of capacitance, more is the quality factor. So for a sharp curve, to get a sharp curve or a better resonance, we should have small value of R. This is one thing. Large value of L and small value of C, of course. So these are the three things that we need to have. Okay, small value of R, large value of L, small value of C, to get a sharp curve, or so to say, for better tuning or better resonance. So this is about your bandwidth and your quality factor. Thank you.